Good morning. Welcome to this Oriental Motor technical seminar. This morning we're going to be discussing AC speed control systems. Just would like to invite everybody who's in the audience this morning to go ahead and type any kind of questions that you might have in the chat section. I will be the only one who will be able to see those messages. And again, feel free to ask questions at any time during this presentation. This morning, I'd like to go over the basics of AC speed control theory with you, mainly Triac type speed control, and we will be covering inverter type speed control as well. First of all, what is a Triac? Just in case you're not familiar with what this electrical component is, basically it's two silicone controlled rectifiers in parallel. It controls current in both directions. So when you use AC power, you can basically control the direction of the current both directions. Now, as we can see, if we look at this little diagram, we see that we have two SCRs in parallel, and this is turned on by this gate terminal right here. Typical applications for this, obviously motor controls. Also used in heating controls and incandescent light controls. When switched on by applying a positive voltage to the gate. So every time that voltage comes, gate voltage comes on, it triggers the diode internally, and this is what general theory of an SCR. Shown here. Over to the right hand side of this slide, we can see these are some typical configurations of SCRs out on the market today. The hockey puck style, and then the stud mounted SCR. So if we look at the actual outputs of an SCR versus a Triac, when we're looking at this diagram here, what happens is usually we're running through some sort of comparator circuit. So when we see the AC sine wave coming in here on the top, when we set the gate trigger level of what actually turns, when to turn that gate on, to turn the SCR on, we see that the output is going to be actually a variable DC voltage. And then in comparison with the Triac, we see that we would actually have two set voltage levels, or gate trigger levels. So the output will actually be variable AC voltage. All of our speed controllers, or at least the AC speed control motors, they all have what's called a Tachogenerator. Now basically what this is it's a device on the back. It involves a permanent magnet and some windings. And as the motor rotor turns, it's going to send back a reference voltage. So in a sense, it's sort of like a somewhat closed loop system. So if we look at the actual circuit or kind of overview of what's going on with our AC speed control systems, we see that, okay, we have the motor here. Now we have that tachogenerator on the back of the motor. That tachogenerator is going to constantly send back an AC feedback signal. That's going to be sent into the comparator circuit. And then, with the reference voltage input via potentiometer, we can then control the phase, or tell the phase control circuit when to trigger on and off, thus sending voltage to the motor. On the right-hand side, we can see, if we looked at in a scope for some waveforms, this would be a typical output. This is showing the comparator circuit, like a sawtooth wave with the reference voltage here, and this is more or less what the output, AC output sine wave would look like. One of the products that we'd like to discuss this morning is the ES series. This is a very simple, low-cost, easy integrated solution for speed control systems. You can use an internal or an external potentiometer to set the speeds. It does have acceleration and deceleration settings, and this controller actually does work with all of our OM type speed control motors. This is a typical wiring diagram of an ES speed controller. If we look up to the top here, this is really what's controlling the control signal circuit for the entire system. We have a switch, a normally open switch to control the run and stop, and then a normally open switch to control the run and brake. The motor would then be wired up to the terminals down at the bottom of the unit, as well as the capacitor, and then, of course, the input voltage. Now, you can control this bidirectionally, but it would require some external switches. This unit does have dynamic braking capability. It does actually control the motor in a speed range of 90 to 1600 RPM. And I actually have a demonstration unit here that I would like to go over with you briefly. Okay, so this is our ES demonstration unit. I'll go ahead and turn the power on. Now this is the actual speed controller here. Underneath here you can see that we have it all already pre-wired up, and there are terminals under here, and then the control circuit is actually going to be controlled by these external controls right here to simulate PLC switching or maybe some ladder logic or whatever you would normally use to control such a device. This box over here is actually a speed output display, and unfortunately you're probably not going to get a very good look at it. But essentially what this does is this takes the Tachogenerator feedback reference and outputs a digital display in RPM. Now this is our V Series induction motor, which is the higher gear life rated and quieter operation type gear system, and much higher output torque. And of course we have the capacitor, since all of our motors do run off of a capacitor. So I'm going to go ahead and turn on the unit. Now you can see, I'll give you a better look, close-up of the motor. Now I can control this speed via an internal or external potentiometer. So I'm going to slow it down with the external pot. Now this does have a 15:1 gear ratio on the motor, so the output speed will be a bit slower. And again, at any time during this presentation, feel free to type in any question you may have. So we have a run and stop switch, a run and brake switch, and we also we can switch between internal or external control. For example, I'm going to go ahead and switch to the internal setting so you can note the difference. The internal potentiometer is actually set to a much lower speed. So I went ahead and turned this back up to the full speed range so we can compare that. Now I'm going to go ahead and turn it to the internal speed settings and note that the speed drops down. So potentially you can actually have two speed settings with this. Now for the next point, I'd like to point out we do have what's called the run and brake and the run and stop. Now if I were to hit the run and brake, I'm going to go ahead and switch back over to the external to the higher speed range. If I go ahead and flip that brake switch, we can see that the motor is going to come to almost an instantaneous stop. So if you have an application where maybe you need to stop the motor fairly quickly, this would be a good unit to consider. Now, when I go ahead and flip the run and stop circuit, when I go to the stop, it's actually going to deaccelerate to where the deacceleration potentiometer is set to. So I'm going to go ahead and flip that switch. So we can see that it kind of comes to a coast. Now I can actually turn that setting, pretty far up, and I think it goes as far as a few seconds actually. So I'm going to go ahead and flip that switch again. I adjusted the potentiometer on the controller itself. So we can see that it comes to a really gradual stop. Oh, and just a note, for your own reference, you can actually, on your screen, you can actually switch back and forth between the demonstration video and the whiteboard at any time. So this is the ESO1 series, and like I said, it's a very simple, low-cost solution. So at this point, I'd like to point your attention back to the whiteboard. Now this is available in input voltages of 100 to 115 volt AC 50-60 Hertz, as well as 200 to 230 volt AC 50-60 Hertz. Now going back to the theory of AC speed control systems, this slide represents or shows a torque speed curve of a 40 watt speed control motor being controlled by an ESO1. Now if we look at this chart, on the Y vertical axis we can see torque, and then on the X horizontal axis we can see speed. Now this line right here actually represents the torque speed curve of this motor. So one thing to note, as the speed decreases, we can see that the torque level does drop out. Now this dotted line up here represents the permissible output torque of the gear. So even at the peak torque range of this motor, we're never going to get above this line due to the limitations or mechanical limitations of the gear. So if you have an application and say you need 10 ounce inches of torque at 1200 RPMs, as long as you're within this safe operation line, the ESO1 can actually perform safely within that limit. We're going to go into general AC motor curves in a moment, but we can note that this is true to typical AC motor torque speed curves. And we do have multiple gear head options available for all our speed control motors. So in general, this is what a typical AC motor torque speed curve looks like. Again, we have speed on the X horizontal axis and torque on the Y vertical axis. So we can see that it's kind of a somewhat gradual inclination and then a quick drop off as the speed increases. Typically, an AC motor is going to run right around in this range right here. If it was just a regular AC induction motor, that's what we would call the rated speed range. And this would also be the range what we give for the rated torque. Now with the speed control type, one thing we do have to realize is since we do have that constant feedback coming to the controller from the motor, the speed is going to be kind of continuously adjusted to maintain that set point. So as maybe the friction or the load increases, the voltage is probably going to increase to compensate for that speed loss to try to give a somewhat continuous speed control. Some design considerations for AC speed control systems in general. We have a couple of curves here to note. This pink line right here represents the input power, and then this yellow line actually represents the output power. And this is within the comparison of the AC motor torque speed curve that we discussed just momentarily, or a moment ago. So, and we also have a power loss line, and then we also have which the power loss is in this light blue, and then we have this efficiency, which is in this green. So if we look at it in a kind of an overview, it really kind of gives us more detail of what's really going on here. We can see that the rated speed and torque point is actually at the maximum efficiency point. So that's kind of where they almost intersect. So we can see that this green line here is the efficiency point, and then that's where we rate the motor torque and speed. Now, also, one thing to note, we can kind of see that as that torque speed curve kind of plateaus, we see that that's at almost at the maximum motor output power point. So these are all considerations that we took when designing this system. So again, this is a 25 watt torque speed curve with an ESO1, and all the things that we noted now might make a little bit more sense to you now that you actually see what's going on here. Again, we have the safe operation line, and then this is kind of the overview of the AC motor torque speed curve in itself. So with that in mind, as we lower the speed, we do have to note that the torque does drop. I'd like to discuss the US series with you now. The US series is a very simple type system as well. We offer it in a package which would come with the controller and the motor. The motor has connectors on it, so it plugs right into the back of the unit. It does have an onboard potentiometer to control the speed. It does have a run-in standby switch to turn it on and off. Very cost-effective solution. And for the theory on how this particular unit works, it's very much similar to what we just discussed with the ESO1 system. Now this is available up to a 90 watt motor. Again, we have a speed range of 90 to 1600 RPM, and as well as multiple gear head options. So when we're looking at the ESO1 or the US series, speed control torque speed curve, we can see that it's very similar to what we just saw with the ESO1 series. This is the typical wiring diagram of a US series. And basically what we have is just your line voltage coming in. We do have to hook up an external capacitor for the 60 and the 90 watt versions. 40 watt and below, the capacitor is actually inside the unit, so you don't even have to wire it up. And really, it depends on how you wire up the line voltage. As you can see, we can make it go clockwise or counterclockwise depending on how it's wired. So potentially, if you did want to do bidirectional, it would require an external switch. And we also do have that speed output option where we can hook up the SDM496, which was that speed display unit I showed you a moment ago. And again, the US series is available in 100 to 115 volt AC, 50-60 hertz, as well as 200 to 230 volt single phase 50-60 hertz. Okay, at this point I'd like to move on to the other type of AC speed control system, which is the inverter or pulse width modulation. Just one thing I'd like to point out before we move on, the pulse width modulation technology is actually very similar to what we use on our brushless DC systems as well. While now it is a little bit different, but theoretically the theory is more or less the same on how it actually works. So what is pulse width modulation control? Pulse width modulation is where we have a reference voltage, and we're going to compare that with a sawtooth wave frequency. And this is going again through a comparator circuit. Now as that reference voltage intersects with the sawtooth wave, we can see that the comparator is actually going to turn on. And then as it intersects back again on the falling edge of that wave, it's going to turn itself off. And repeat it over and over and over again. So as we manipulate that reference voltage, we can see that we get different outcomes. If we were to lower that to hit the sawtooth wave at a lower point in the rising edge, we can see that the on time actually increases. So we can manipulate that on time to different timings, if you will. This is the output of a typical pulse width modulation circuit. We can see with the short on time, with this noted by this wave up here on the top, that the average voltage is a lot lower. But if we were to increase that on time, we can see that the average voltage then becomes much higher. So, with keeping that in mind, what is the purpose of an inverter? An inverter, or really noted a lot in the field, a variable frequency drive, pretty much can control the speed, torque, and direction of an induction motor. It does take a fixed voltage, fixed frequency AC input and converts it into a variable voltage, variable frequency AC output. It does output in a three-phase sequence. Now this is possible due to the fact that the speed of the motor, N, is equal to 120 multiplied by the frequency divided by the number of poles. Now internally in the inverter control circuit, there is a microprocessor that does take care of all the internal logic decisions. So this is a typical circuit of an AC inverter. We can see that we have 6 transistors being output to a three-phase winding configuration. For all inverters, we do use a three-phase type motor. Now, according to this timing sequence, and this is again controlled by the microprocessor, we can see that there is a sequence to where these transistors actually turn on and off. For instance, if we were to look at the first sequence, we can see S1 turns on, and then we can see that S3 and 4 then turn on. So basically there's always going to be 2 windings on at a time, and we can note that there is a phase angle difference of about 120 degrees. And basically what that means is that it is outputting 3-phase voltage. So after it passes the voltage passes through this inverter control circuit, if we were to look on a scope, this is what we would actually sort of see more or less coming out of the inverter. So we can see here that we have a short on time, and it gradually increases and kind of peaks in the middle, and then around 180 degrees it kind of comes back down. Now this signal is actually inverted, changes polarity, and does the same pattern again until 360 degrees. So if we were to look through a scope, over here is what we would actually see being output to the motor. Now if we zoom in really close, we can see that it almost looks sort of like a digital AC sine wave, and in a sense that's exactly what's going on. We've manipulated a DC signal after converting AC to DC and then inverting that signal. Using the pulse width modulation circuit, we've actually kind of artificially recreated an AC sine wave. And this is how we're able to control the speed in a very effective way. Thanks again for your patience. All right, so we're going to move on to the different inverter types that we currently offer. The first inverter type would be the BHF Control, and this is just a general type inverter. So as we can see, as we vary the frequency, we actually manipulate the torque speed curve. So at 40 hertz, the speed is going to run at a much lower speed, again, when referencing the torque speed curve. One thing to note, though, is that we do actually have somewhat of an increased output torque. So, and when we compare that to the 60 hertz curve, we can see that while the speed does increase, we do see a drop in output torque. So in this example is kind of expanded upon the point we just made. Every time that we adjust the frequency going out to the motor, we can see that the torque speed curve changes not only in speed but as well as in torque. Now, one of the products that we currently offer is the inverter with a torque boost. Now, with this torque boost built-in feature, we can see that normally as we lower the frequency, eventually at the very lower points, the torque does actually start to drop, even though the speed, typically when we lower the speed, it drops, but there is a point where we can see that actually the torque starts dropping as well as the speed. Now with this torque boost, we can see that that torque is actually somewhat maintained by manipulating the voltage that actually goes to the motor. An example of this is actually the FE100 series. The FE100 series inverter is for motors up to 100 watts. We actually have what is called the FE200, which can be used up to a motor of 200 watts. It can be controlled by external DC voltage, 0 to 10 volt DC input, and we can see that it does actually have a digital display. Now you can either display the output speed of the motor, or you can display the frequency being output to the motor. This is kind of an overview. If we look behind the front panel cover of the FE series, we see that we do have the onboard potentiometer. This setting here is actually to adjust which wattage motor you're using it with conjunction with. Now you can set gear ratio settings. Say if you do have a gear on your inverter, or on the motor, excuse me, you can put in the gear so it'll actually output the actual output speed of the motor. And we do have acceleration and deceleration potentiometers. We can control the direction via this switch underneath the cover, and we do have a run and a standby switch. Now keep in mind, we do offer many different types of three-phase motors, and we do have literally hundreds of gearhead options available. So if we look at the torque speed curve characteristics of the FE series, especially when we remember the Triac control type speed controller, we see that we actually have a much wider torque speed range. Again, as the speed does increase to the upper limits, we see that the torque does drop down. And we also see that we have kind of a gradual decrease in this speed range. But however, for the majority of the speed range, we see that we have a somewhat flat torque speed curve. Now this does have a 200 to 2400 RPM output. Now this is a diagram of the FE wiring. Now we can see here that we have the line voltage coming in, and then the output phases to the motor. And to control the inputs on this, really all we're doing, if you want to control it externally, all we're doing is completing a circuit to a common ground. So we have an internal voltage supply, and once we complete this circuit, we can see that the unit actually, the input, excuse me, would actually be activated. Now I do have a demonstration unit that I would like to show you briefly. Now this is an FE100 series inverter, and actually we do have two FPW motors. Now these are washdown rated motors with 5-to-1 gear ratios. Because this output's two-phase, potentially you can hook up multiple motors to this inverter. Typically, we wouldn't suggest you to put more than 2 of them on here. Since this is a 200-watt rated inverter, we can easily hook up 2 40-watt motors, and this inverter can handle it. So I'm going to go ahead and turn on the unit. So we can see this is outputting to both motors, so theoretically the motors are going to run in sync. Now we can control the speed via this onboard potentiometer. Now keep in mind you can actually send a 0 to 10 volt DC signal to control the speed as well. We take a closer look. Oh, excuse me here, just one moment. I actually wanted to take a let's take a look at the FE here. So we can see that it actually does display the output speed of the motor. So as I turn this up, we can see that the speed does increase. And we have this run and standby switch here to turn the motors off. Now this can also be wired up externally to turn the motors on and off via the external I/O as well. I do have a switch mounted here externally so I can reverse the direction of the motors. Now this does have onboard potentiometers to control the acceleration. Right now I have them turned all the way down. So if I go ahead and flip this switch, we can see that the motors reverse directions. Now because this is a 3-phase motor, these motors can practically reverse directions almost instantaneously. Mounted on the output shaft are a couple of our dampers, and we really just mounted these simply for demonstration purposes. Again, these motors are IP65 rated, which means they are completely waterproof and dustproof. And this is a very common way to control the speed of these types of motors. One thing to show that we can get down to a really low speed range with these. Now, again, I'd like to invite the audience, if you do have any questions regarding this product in general, or any questions that may have arose so far, go ahead and feel free to type those in. All right, at this point, I'd like to bring your attention back to the whiteboard. Now, as far as input voltages go for the FE100 series, we can put in 100 to 120 volt AC 50-60 Hertz, 200 to 240 volt AC single phase 50-60 Hertz, as well as 200, 240 volt AC, 50, 60 hertz, three-phase voltage. Another type of inverter that we offer is an open loop frequency boost control. Normally, and this is with AC motors in general, once we set a speed, since there's no feedback, if there's a fluctuation in the load or increased friction, the speed is actually going to drop down. And this is simply the way that an AC motor works. There's slip involved in the process of motion. So as the load increases, we can see that the speed would then drop down. However, because of this frequency boost control circuit, and this is actually featured on the BHF series, we can see that the controller or the inverter would sense this, and this is based off of a current setting or a current reading, would automatically compensate to increase the amount of voltage or increase the frequency going to the motor, and therefore bring the speed back up to the original set point. And this is used on the BHF series. Now this is a 200 watt or quarter horsepower AC speed control system. We do have right angle shafts available, as well as hollow shaft and parallel. This would come with a dedicated inverter or driver. The right angle gears are actually hypoid gears. If you're not familiar with hypoid type gears, they're actually very efficient. We can output a very large amount of torque. There are magnetic brake options available, and the BHF series driver actually can control the on and off operation of the magnetic brake. And that's something not standard with the FE series inverter, which we discussed, or the US or ES series. It does have an internal or external potentiometer control capability. It can hook up an external DC voltage. It does have directional control as well as dynamic braking. Now, because of this this control circuit, or this current reading circuit, and because it automatically compensates for the speed when the load or the friction increases, this does have a plus or minus 3% speed regulation. And for an AC motor, that's actually very good, considering that our brushless products are typically around the plus or minus 1% range. It does have an extended speed range, or at least an extended torque speed curve. And we can see that on this curve, it's actually very flat through the typical speed range of 100 to 1500 RPM. So a very, very good feature to have for the flat torque speed curve. So again, when you're operating anywhere within this region under this top line here, we can see that the motor is going to be able to handle the load. And as the speed does increase, we do see that the torque does eventually drop down. This is a wiring diagram of the BHF series. Again, looking closer at it, we can see all we're really doing again is we do have an internal voltage supply, and we're just completing circuits. We can control the direction, stopping and starting, speed setting method, internal or external. We do have a slowdown input to gradually coast or to stop according to the deacceleration settings. And we also have an external magnetic brake release feature. Again, we can send that 0 to 5 volt DC signal to the driver to control the speed, as well as hook up an external potentiometer. Now, this is available in input voltages of 100 to 120 volt AC, 200 to 230 volt AC single phase, as well as 200 to 230 volt AC three phase. We do have a right angle hollow shaft, a right angle solid shaft, parallel shaft types for the gear, as well as a round shaft type. This is an overview of all of our speed control systems. The bottom in the pink section is what we just discussed, which is the AC speed control systems. On the top in this yellow area is the brushless DC systems. So we can see here that for the most part we do have a wide speed range with the AC motor systems. Just to point out though, we do have an much extended speed range when noting the brushless DC systems. And there are some differences. And oh, I'm sorry. Question: do you have inverters that output range of 30 to 50 volt AC? So you're looking for single phase output frequency. Oh no, actually, right now we do not have inverters that output single phase of 30 to 50 volt AC. Was this for a particular motor that you were interested in, or, you know, because typically most inverters are always going to output three-phase. I know there are a few that here and there they're kind of scarce, but yeah, I have heard of some that do actually output single-phase. Typically, that's not what we really get into here. All of ours are definitely going to output three-phase. But that's in an interesting voltage range of 30 to 50 volt AC. Was it still going to be, if you don't mind, the customer who's asked the question, if you don't mind, you also need to control the frequency as well, or is this straight AC speed control, a variable voltage? Well, if you don't feel comfortable answering the question now, you know, we can definitely. Okay, it's students' experiments on inverters. Yeah, I'm not really sure where you could really go for that. We don't actually offer that. I have heard of it before, but it's uncommon. I guess if it's for students, it would probably be a good project to maybe make a circuit to do something like that. I'm sure that would be fun. But no, unfortunately, we don't offer that, to answer your question. All right, well, at this point, the presentation is pretty much wrapped up here. And I encourage you, if you do have any questions, you can feel free to call this 1-800-GO-VEXTA number. This is to the Oriental Motor Tech Support Team. And we're all qualified to answer any questions that you may have. Also, if for some reason you would like a copy of this presentation, go ahead and call up and we can definitely make that available for you. And I would like to thank you for coming out this morning with us and learning about our product and some speed control theory. And again, thank you for signing up. Have a good day. Oh, price range of inverters.